Okay, so what topics would you guys like to cover? We have limits, continuity, derivatives, applications of derivatives, and the stuff we did last time, differentials and business applications. What's that?
Do limits first.
Limits first? I'm kind of inclined to do limits first and then do the business applications and maybe do the derivatives last if we get to them, because I think those are, maybe we'll do the harder ones but not kind of the easy ones.
Yeah, that works.
Okay. All right, so let's start with limits. Okay, so limit as x approaches to 3x over x plus 1. What's the first thing you always do when you do a limit? Plug it in. So if I plug in 2, I get 6/4, 6/3. I can't do it. A little ragged this morning too. So this is my answer. You plug it in, you get a number, you're done. What does this suggest about continuity? When I look at this, is it a vertical asymptote? No. Am I looking towards infinity horizontal asymptote? No. Is it a hole in the graph because I had something canceled? No. So it's not a cusp, it doesn't happen. This is continuous right here. There's nothing unusual about that. It's not anything weird. Okay. Okay. And we really need the graph of that to know that it's differentiable, but it's also differentiable. We don't know how to do it yet, so don't worry. We don't know how to do any derivatives except the ones that are x to the something in the numerator. That's the only one we know. All right, so let's look at this one. Limit as x approaches 2 of 3x over x minus 2. So the first thing we always do is try and plug in. So when we plug in, we get 6 over 0. So anytime you get a number over 0, what do you know?
Vertical asymptote.
It's a vertical asymptote. What? So this, any number over 0 tells you vertical asymptote. What do you know as vertical asymptotes? What is the function doing? Well, it could be going like that, or like that, right? It could do any of those things. Well, except this would be at 2 instead of 0. But so it's going to plus infinity or minus infinity. You just don't know which. So you could actually write plus or minus infinity. The thing you have to figure out now is which one. Because that's 2 answers. You can't have 2, you need to have 1. So, I treat this like a sign chart. So, if I'm treating this like a sign chart, I'm really just considering what happens on either side of 2. So, go ahead and put 2. Let's go ahead and actually write a sign chart with just 2 on it, because I'm only interested in that part. Because I know it's going to either plus infinity or minus infinity. I just need to know the plus or the minus. So the thing that I need to do here is I need to consider the right versus the left, and then look on either side. So we'll have the limit as x approaches 2 from the positive side, and the limit as x approaches 2 from the negative side. And why am I doing that? Because it's a vertical asymptote. I know it's screaming off to infinity, I just don't know which one, so I have to treat the 2 sides separately. Okay, so if I'm just on the positive side of 2, I'll get a positive and a positive over positive, so I get a positive. If I'm on the negative side of 2, like 1.9, positive, negative, so positive, negative, it's negative over here. So now I know exactly what my limits are doing. From the right side, it's going to infinity. Which one? Positive infinity. From the left side, what do I have? It's going to negative infinity. It's negative on this side. I know it's infinity because when I divide by a tinier and tinier and tinier number, the value gets bigger. So I know it's one of the infinities. So now, my original problem was about a 2-sided limit. What do I think about this? Do they agree or not agree? They do not agree, so the 2-sided limit doesn't agree. Okay, so this one, they do not agree. So the 2-sided limit does not exist, I should say. So the limit as x approaches 2 not exist. It does not exist, not because of the infinity, but because one's positive and one's negative. If I had x minus 2 quantity squared for my example, then both sides would be positive. It'd be going to infinity from both sides, in which case I'd know exactly what was happening. From the two-sided limit from both sides, it's going to infinity. I would know that. So this does not exist is all about these not agreeing. So far, so good? Okay, so you always try and plug in first. You get a regular number, you're done. So let's talk about continuity here. Is this one continuous?
That's not.
This one's not. Why not at 2? Because I'm going to two different places.
It's a hole.
This is not a hole. This is a big giant gap because this looks, something like that. There's just a big gap. It's not a hole. It's a, I guess I call it a gap. Okay, so let's look at another one. So would it be differentiable there? If there's a big gap, is it differentiable?
Yes.
No. You have to have continuity in order to be differentiable. All right, so let's look at this one. Limit as x approaches 2 of x minus 2 over 6x squared minus 12x. So why don't you guys do that one? First thing you do is try and plug in. And then tell me what you get when you try and plug in.
Zero.
0 over 0, I think. 0 over 0. That's called an indeterminate form. And why is it indeterminate? Because we don't actually know what this value is. Any other number over 0, 2 over 0, 10 over 0, a million over 0, I know that's going to infinity, but 0 over 0, I don't know what it's doing, which means I have more work to do. And for us with polynomials, it means what? What's the more work I need to do?
You need to factor it.
Factor it. This is going to be a whole. And what it's saying is that the value in the, oh, let's just do it. So you're going to need to factor this. I would consider this to be an easy factoring for a test. What's the first thing you always do when you factor? Pull out any common term. So 6x, x minus 2. So if you find that you're really having trouble factoring a problem on the test, there's probably something that you're missing, because this should be easy. Okay, so these cancel. So really, this is the same as the limit as x approaches 2 of 1 over 6x. Is this a vertical asymptote? It's got an x in the denominator. Everyone thinks it's a vertical asymptote. Is it? Plug in 2, right? That's the next thing you do. So I plug in 2, and what do I get? 112. Is that a vertical asymptote? No. What it is it's a hole in the graph. So what this means is at this point x equals 2, the y value is 1/12, but it's a hole. Yes?
I'm guessing it's probably algebra, but how come you can't just cross out the x minus 2s
That's what.
I did.
as a whole?
Oh, yes, I'm sorry. Yeah, I didn't get it through the x. Yes, I apologize. Yes, the whole of it, yeah, I just didn't draw it very well. Yeah, no, thank you for checking. Yeah, so this is a hole. So is it continuous at the hole? No. No, because it's a gap, right? It can't be continuous at the hole. There's nothing there. So remember, continuity requires that the left limit equals the right limit equals the actual value of the point. So if the value of the point isn't there, then this, you need all three pieces. So it's not continuous here, and because it's not continuous, then it's not differentiable either. Differentiability requires continuity. Okay, so let's look at, so far we've been looking at limits as x approaches a finite number. You always try and plug that in. Now let's look at one as x goes to infinity. So here's the limit as x actually goes to negative infinity. 6x squared minus 12x cubed all over x to the fourth minus 2. This can't be, I mean,
I'll just switch it on.
okay. Maybe the testing center? No? Okay. Okay, so limit as x approaches infinity. First thing I would try and do is plug in and I get some infinity over some infinity, right? Do I know what infinity over infinity is? No. Okay, so if you tried to plug in, you get some weird infinity over infinity. Just like 0 over 0, we don't know what that is. If it were if it were 4 over infinity, I know what that is. That's 0. I take 4 cookies and divide them into an infinite number of kids. Each kid gets the tiniest crumb there. It gets nothing. So I know what this is, but I don't know what that is. So how do I handle this one?
It's like indeterminate form, so you have to like factor, right?
No, there's no factoring in this one.
Okay.
I mean, yes, that's a reasonable thought, but in this case, no. Because I'm going to infinity, how important is this 2 when x gets really big? Yeah, no.
Like
And really, how big is the x squared compared to x cubed? When I'm up to 1 billion, this one's 1 billion times bigger than that. When I'm at 1 trillion, this one's 1 trillion times bigger than that. So this is one where you're looking at leading terms. So anytime we're looking at this, when you're getting really huge, the only thing that matters is the biggest piece in the numerator and the denominator. So here we're looking for leading terms. Please note that leading terms are not the first term, it is the term of the highest power. In this case, it's written out of order. So we're going to take this term, including the negative sign, and this term. Those are our leading terms. You have to include negatives particularly. So limit as x approaches negative infinity, negative 12x cubed over x to the fourth. Are these two functions exactly equal? No, of course not. But when you get way out to infinity, they are acting the same way. So that's because remember, acting, behavior, that's what limits are about. It's not about the exact value. I don't care about that. Okay, so now once you've gotten here, simplify this. Do the complete simplification. So what do you guys get? No, I mean simplify, just keep the, we haven't done the limit yet. Just clean this up, simplify that. Yeah. Negative 12 over x, the x cubes cancel. Okay, so now I try and plug in again. So when I try and plug in, I'm going to get negative 12, I mean if I could put in negative infinity. Right? The reason that it's important to think about this, even if you don't really write it, because of course this doesn't really make sense. The minus signs cancel, although in this case it doesn't matter. 12 over infinity, any number over infinity is what? 0. 12 cookies, an infinite number of kids. No one's even getting a crumb. Okay, so that's... Okay, so we have two different sort of categories of limits. One is x approaches a finite number, and then a separate way of handling it is when we have x approaching infinity. What is this describing? If I want to know the limit, what is the function doing? Remember, this is the function. What is the function doing as x goes to negative infinity? What am I describing here? Right, so it says, wait, I don't know, I don't care what's happening out here, right? It could be doing anything here, but when I'm going way out here, I'm going like that. So when behavior is like this, when it starts hugging close to a value, what do we call that? An asymptote. And in this case, it's a horizontal asymptote. So this is the horizontal asymptote. The horizontal asymptote for this function is y equals 0. Remember to write your points as ordered pairs and your asymptotes as don't write this. I know what you mean, but it's kind of like text talk. It's not very precise, not very formal. So this is correct. All right, one more on limits. Oh, so differentiability, that's not really a question we ask here because we don't really have a point, but really as this function is going out this way, it's a regular rational function. There's no reason to expect that it's not continuous out here or differentiable. All right, so one last one. two left ones, and a 2. So these last two are where you need to either pick from the graph or from a piecewise definition which definition to use, right? So let's start with this one. Let's start with piecewise. So if you have f of x equals the square root of x plus 1, or x squared plus 2, and so you're going to use this definition if x is less than 3, and you're going to use this definition if x is greater than or equal to 3. So, and then we'll look at two limits. Limit as x approaches 2 and x approaches 3. On a test, I'm going to want you to indicate to me which definition you're choosing. So don't just write down the answer. I'm going to want it. You could even just write down the, off to the side, square root of, somehow show me how you got your answer. So here, as x approaches 2, which definition will I use? Where does 2 fall in this? Is it in the x less than 3? Yeah, it's in the first one. Is it x is less than 3 because it's 2? So that means that this is really this. As x approaches 2, square root of x plus 1. Because when x is near 2, that's the function definition I'm going to use. So the first thing I always try is plug in. Square root of 3. Is that a regular number? Yep, we're done. Okay, so that one's easy. So now let's look at x equals as x approaches 3. Remember, limits are about what? Exact value or behavior? Behavior. So I need to look from the left and the right. So particularly here at x going to 3, the actual value is going to fall in this category, right? The actual value is going to be from this one. But I need to check, since I'm looking for behavior, I need to check from both sides because it's a two-sided limit. So we need to look as x approaches from one side and the other. And this is really only a problem at the place where the two definitions meet. Normally that's the only place you have a continuity problem. So from the positive side, which definition will I choose? Where is x slightly greater than 3? This one is slightly greater than 3. So this one is the one that goes with this. X squared plus 2. And when x is slightly less than 3, which definition? Slightly less than 3 is going to be in this category, so I'm going to pick this one. And then do some plugging in. Plug in 3, I get 9 plus 2, 11. Plug in 3, square root of 4 is 2. So for this piecewise definition, are these two endpoints going to meet up? No. The actual point will be here. The actual point will be 3, 11. That will be the xy point, but they're not going to the same place. So the two-sided limit then, I guess we can come down here, this two-sided limit does not exist because the two ends don't meet up.
Why would you choose to do that for the first one as well?
Because there's no reason to expect that I have a problem here. I know that square roots are continuous, right? As long as I'm in the domain, I don't have any reason to expect anything different. What do we say again?
Just because of the way the limit is written.
Right. I mean, square root of x plus 1 looks like that, right? Looks like that, and that says shifted to the left by 1. So I know it looks like this. So around in this area, do I have any reason to expect any continuity issues? No. So I don't need to check left versus right. Yes?
Where did the 2 come from, the limit as x approaches 2?
This one?
Yeah.
I made it up. Oh yeah, these are my two problems. Yes, so number one, sorry.
It'll give it
Number
to
one
you in the...
and number 2. These are two separate problems that pertain to this. Yeah, sorry about that. Yeah.
Okay, so anytime you have like an equal to or something, you always need to check to make sure that they meet the same point. No,
So in,
no, with the limit.
oh, here.
Yes, so if you're, is it going to give you and say you need to check the two-sided, or are you going to have to figure that out on your own?
If I give you this,
Yeah.
no, I'm not going to tell you to check the two-sided limit. You'll need to figure that out.
Right.
And so for this one, anytime you're looking at a piecewise function and you're asking a question about that point where they meet up, you know you have to check left versus right, because the definitions are totally different on other sides. So they might meet or they might not. So anytime that you are checking the kind of the meeting point of the definitions in a piecewise, you have to check both sides. In a case like this is squarely, x equals 2 is squarely in this definition. Do I have any reason to expect that this is not continuous? No, I know what that looks like. It's So this is why I asked you guys to know some functions. So go back over your minute to win it list. That's all the information you should know off the top of your head. So if you know what this looks like, and you know this is a shift to the left, I mean, really, that's as much as you need to know in your head to know that I don't have a problem at 2. It just is, you know, same thing if I wanted to know the limit as x approaches 4 of x squared minus 3x plus 2. What kind of a function is this? It's just a polynomial, right? It's going to go up and down. I don't know. Oh, this one actually does. Does that one factor? That one actually factors, right?
Yeah.
So this one is x minus 2, x minus 1. So if you wanted to graph it, you know it goes through here. So do I have any reason to expect a problem at x equals 4? No, I don't even need to graph it. This is a polynomial. Polynomials just go up and down smoothly. There's never a problem ever with a polynomial. So there's some functions that you know you just never need to check right and left because they're continuous, they're smooth, they do behave nicely. So when do you need to check right versus left? There are 2 main cases. Here, piecewise, and vertical asymptotes. Same problem because you don't know if they're meeting up or not. So anywhere where you expect the 2 sides may not match. So really vertical asymptotes and piecewise, those are our main ones. That's when you need to check left versus right. Do we need to go over picking out limits from graphs? Yeah? Yes?
Yeah.
Yep, okay, we'll do a couple of those, and then we will move on. Okay, so let's say I give you this, totally making this up. Yeah, we'll just do this. Okay, so if I'm interested in the limit as x approaches, so I'm not going to write all the limit over and over and over again, but if I'm looking at x approaching -2, what will the limit be? One way to do that is to draw a dotted line at x equals -2. And now look and see what the function's doing as it's approaching that line. Where is it going?
0.
0. Is it continuous?
There.
Yeah. Is it differentiable?
Yes.
Yeah, it's a straight line. So in this case, for this one, no problem. All right, so what about as x approaches -1? So again, if you want to, draw a dotted line through the yeah, there are a couple of problems, right? There's a big gap, for one thing. So does the 2-sided limit exist? No.
No.
So again, if you draw a dotted line at the x value of interest on the graph, then just look at what the graph is doing as it gets close. And remember that the answer to a limit is a y value. So here's your x value. What's y doing? Well, from one side it's going to 1, and from the other side it's going to 2. So does the 2-sided limit exist? No. So is it continuous? No, there's a big gap. So if it's not continuous, then it's not differentiable either. All right, so let's look at x approaching +1. So again, you can draw 2, sorry, x approaching 2. So behavior-wise, what's the function doing from this side? It's reaching 2. And what's it doing from this side? Reaching 2. So this, the answer is 2. Right, that exists. Is it continuous? Yeah, right versus left, the point is there, all's good. Is it differentiable? Remember, the derivative is the slope. Is the slope from the left and the right the same?
No.
No.
0 and whatever that is. And they meet at a point. So if it meets at a point, so a point, that could be a point or something like this is called a cusp. If the 2 sides don't have the same slope, then we say the derivative doesn't exist at the point. Because which slope would you pick? There's no way to tell. So this one is continuous, but not differentiable. Differentiability is not something that's a big part of the test, so don't spend hours working on that. Might be a point. Okay. right, so I'm going to call that good on limits. What else would you guys like to, so we have sign charts. Let's save that for the end, because that's something that, like I said, I have some good resources online that actually have videos of going through sign charts, so if you're still stuck on those, let's hold that for the end. Do you want to do some derivatives? Do you want to do a difference quotient? Yes?
I got a question. If
Yes.
I find it that, would you mind doing?
No, that's fine.
Let me see if I can find
All right, you look and we'll keep working on some other ones. All right, so let's look at let's just look at derivative forms to make sure that you know what to do with derivative forms. So I'm going to list a few different functions going down here, and we're going to put the derivatives in a second column. And I'll change the letter name so that we're all straight. And actually, we'll use different formats, because remember, there are different ways to indicate derivative. This is one of them, F prime. That's not a 1, it's like an apostrophe, a prime. So if I have this, do you look at that and say trivially easy? You should, right. So this is just 2x. It is already in the correct format. The correct format is x to an exponent or a constant. That's all we know how to do so far. We'll get more next time. Next week, we'll have more. All right, so what about this one? Is it ready to go for the derivative for all the pieces? No.
No.
This one's good, right? We don't care about 2.3, that's fine? What about this one?
Well, that's 2.3.
That's a 2.3, yeah. And so this is minus 1 over x. I can't do it this way. I have to have an x to an exponent. So how do I rewrite that? X to the minus 1. And I recommend that you rewrite the whole thing. Don't take the derivative of the first piece and rewrite the second piece, and then in another step take the derivative of the second piece. Do your derivative all in one step. So rewrite in one step, derivative in one step. If you had a 4 down here, where would it be in the rewrite? It stays in the denominator. Nothing, it doesn't move. The only thing I need to move is the x. 1/4 is still there. So if there were a 1/4, if there were 4 in the denominator, that stays. So you can kind of think of it, that's your number that's out front of the x. Okay. So I'm going to take that back. Well, I'll take it back out just because it's not in the answers, so in case you go back. So derivative then. What's another way to write this? I could write d dx of that. D dx is an instruction that says take the derivative with respect to x of this. Okay, so 4 times, remember multiplication carries through, addition, subtraction carry through, so you just write 4 and then the derivative, minus and then the derivative. So 9.2, x to the 1.3. I just multiplied 4 times 2.3. Minus derivative of this, -1, x to the -2. And then clean it up. Okay, don't leave it that way. Clean up the numbers. Okay, what about this one? What if I tell you find dy dx for y equals x times x minus 2? Is that in the proper form for now? I can handle multiplication by a constant, addition and subtraction. Do I have anything more than that? Yeah, I have more than multiplication by a constant. So what do you have to do here? Multiply out. The answers are online, so I'm going to keep moving just to make sure we have time to get to some of the other harder stuff. And what about this one? What if I say to find y prime for y equals 4x minus 2 over x? Is that in the proper form? I need just x to the something. I see a fraction. I see a rational expression with x in the denominator. No, this is nowhere near ready. So this one I could multiply out. This one essentially I can divide out. I can go ahead and separate out the fraction. So I'm going to